Hi everyone, we're very happy to have Chris here to present his work. Chris is a PhD candidate in computer science at Stanford University, advised by Professor Jeanette Bog and Professor Marco Pavone. His work focused broadly on reliability, interpretability, and composability of policies toward advancing general-purpose manipulation capabilities. He is a member of Stanford Artificial Intelligence Lab and the Center of Research on Foundation Models. Pass the time to Chris.
Thank you. Thank you so much, Roger, for the introduction. And it is both a pleasure and an honor to present some of our recent work at your lab meeting. It's also nice to see some familiar faces here. So yeah, as Roger mentioned, I'm a final year PhD student, soon to graduate. Have been working on various topics throughout my PhD, more recently on guardrails and interpretability, which is what will be the focus in today's presentation. But where I'd like to start is really starting by acknowledging like the huge investment that's being made in robotics data collection and amassing of trajectory data of various different forms, either through like collaborative efforts where we pool data or like large scale data collection efforts spread across academic and industrial labs like Droid. But then also, data algorithms that try to ingest subsets of these data and like perform augmentations to increase their scale and diversity and do other things, other interesting augmentations to these data sets. Really looking at like all these different efforts as like a combined way of building a data foundation on which we can scale the training of larger and larger generative policies. And then often doing so, not using the most like complex, sophisticated algorithms out there, but using simple algorithms. Supervised learning, right? Behavior cloning seems to be like an ingredient set that's what the industry is like really honed in on at the moment, and is one that is allowing it to scale. And really, like when these elements come together, we're seeing some impressive results. Like for example, here's Pi Zero, slightly outdated, but I think was a really nice result when it was released, where you see that like we now have one, you could call it like one recipe that you could follow to unlock progress on tasks with like greater and greater amounts of dexterity, interesting dynamic complexities, where you could not imagine, the amount of effort required to like hand define controllers and like reward functions to solve each of these tasks independently, right? So this scalability is like a big advantage we're getting with this new paradigm. At the same time, right, if you've worked with these policies, you know that they're not perfect. So they exhibit like all sorts of weird failure modes. And it's not just that they fail, but it's really difficult to predict when they would fail. So if you look at like the initial states between the successes and failures, it's like sometimes it's the most subtle of variations that may cause failures or like unexpected behaviors. And really what I want to forward here is that like now that we're in this data-driven paradigm, you cannot really separate the performance of your system from the training data. That like really performance and behavior of your model, it really depends on like idiosyncrasies of your robot training data. So by idiosyncrasies, I mean like everything from data coverage, right? So you talking about like out of distribution failures from these policies. Maybe your data doesn't have enough coverage for the sorts of configurations of the initial state that you're looking at. But it could also be like other things like data quality issues and so on and so forth. And really when you want to like start approaching these problems of addressing robot failures in the large scale data driven learning paradigms, you have to be thinking about things in terms of data and through the lens of like what's going on between the deployment domain, the behavior of your model, and the data it's been trained on. And so toward that end, we've been doing a bunch of different works on this topic, but the two that I'm going to like briefly go over today are first guardrails and then interpretability. So when it comes to guardrails, we're asking questions like when do policies fail? Can we figure out when they fail? Can we start to categorize and define failure modes for these generative policies, which is often involves the development of new runtime monitoring and failure detection algorithms. And then on the right hand side, interpretability, we want to start asking questions like, okay, what is causally driving these failures, in a way that allows us to actually improve policy performance rather than just like catch fault policies when they're faulting. And for this, we start looking at like data-centric interpretability tools and the role of data curation. And really, I'm gonna just very briefly touch on guardrails, almost as a sort of motivation to talk about the work on the right hand side here today. And so when it comes to runtime monitors, we had a work that we presented at Coral 2024. It's called Unpacking Failure Modes of Generative Policies, where the basic setup there is what you'd expect from a generative imitation learning setting, where you start with something like a diffusion policy that predicts a sequence of actions. And then, for the sake of like simplifying the problem setup, considers a single task setting where you may want to like teach a robot how to close a box with three lids, right? And so you'll collect some demonstrations, and you'll train your policy using imitation learning. And then, I'm assuming that like most people in the room kind of understand this like receding horizon rollout when you have action chunks where, you predict a sequence, but then you only execute like the first few actions before predicting the sequence again. And so if you have a sequence of like four actions that you're predicting, but you're only executing one, your rollout kind of looks like this over time. Um, but after you've trained your policy, you might like validate it on some nominal test cases in your lab, right? And you find that it works, which is great. So you like you're happy that you have diffusion policy working, for example. Of course, the challenge comes like when you deploy your policy in like slightly more varied environments, right? Where it's doing well most of the time, but every now and then it reaches a test case that like really challenges and causes it to like do something unexpected. For example, in this case, like the policy just stalls for some reason and doesn't move on to the next stage. And then what you'd like to do is come up with a sort of runtime monitor that can detect failure at the earliest possible time step. And the other thing is that like failures don't always repeat themselves in the same way. So that's why there's this element of like detecting unknown failures. So the failure that you saw yesterday may not look like the failure you saw today, and so it's actually really difficult to start using failures as training data to detect new kinds of failures in the future. And so I think the key observation for us here within the context of the presentation is that we were finding in like some of our toy experiments that these policies, when trained on heterogeneous demonstration data, so demonstration data that solves the task in with like a higher degree of variance, failures don't always come in the same way. So it can result in highly diverse failure modes. Like you have these failures where the arm just collides with the box. You have these failures where, the policy exhibits like really unsafe, like high jitter behavior, which you would definitely not want to happen on your robot. And then you have like stalling. You have cases where the policy just like stalls and then like pulls away from the box. And like given the training sets that we were using, it was like really it was really difficult for us to like figure out what we would see and why this was occurring. And so like the core idea for us in this paper was that given the diversity of these failures, it's actually quite difficult to come up with a one size fits all or like a catch all kind of failure detector. And so you're better off sort of splitting failures into complementary categories or failure modes, let's say, and design specialized detectors that are better suited to the specific requirements of these different failure categories. Like, for example, on the left-hand side, you have failures that occur, fast. So we call them erratic failures. These are ones that you don't want to wait out to find that the policy is not making progress on the task anymore. you want to catch them as soon as they're occurring to like prevent damage to the environment or to the robots themselves. For this, we came up with a more of an output monitoring kind of detector, the details of which are like not super important, but it's essentially looking at like the temporal consistency of the policy. So are the actions that it's predicting now sort of consistent with the actions that it thought it needed to use in past time steps? And then on the right hand side, with these sort of slower time scale failures, which we call task progression failures, you really need to reason over time to figure out that the policy is not making progress within the context of its task specification, which is something that we felt like vision language models would be pretty well suited for, and increasingly so with like video language models just improving more and more over the years. And so we came up with an overall failure detector that starts with the policy rollout and essentially runs both both kinds of specialized detectors in parallel. So you have the temporal consistency detector, which is sort of computing distributional distances between the policy's action distributions over time throughout the rollout. And you have the VLM that is reasoning over the video and the prompt as to whether the policy is like continuing to make progress on this task. And then you can issue a warning and execute a stop if either of these failures flag, right? Or either of the detectors flag failure. And what we saw is the key takeaway there is that like this divide and conquer strategy is actually something that works quite well across like a few different metrics. So first and foremost, if you go from just using orange, which is your temporal consistency detector, the one that's like catching failures fast, to using both, you get a 40%, 48% improvement on our data sets when you combine it with the VLM, which is in green. Of course, the delta between using the VLM alone and using both isn't nearly as large. However, the VLM is like a lot slower, and so when you look at things like detection time, so how long into the rollout until your runtime monitors are issuing warning, you see that you get like massive improvements by combining these two, right? I think like 35, roughly 40% improvement in detection time. And then naturally, like when you combine detectors, the false alarm rate of the overall system is like a combination of the sensitivity, right, of both individual detectors, and so you do get like a small increase in false alarms. That said, like we took a very like preliminary approach to combining detectors where we issue a warning if either of them do, right? It's a logical or, and I think there are perhaps some more like sophisticated ways of combining detectors in the future. But all that to say that returning to like our example of these failures from large scale VLA type policies, we can ask questions like when are failures occurring, and even in the future have runtime monitors describe to you in language like what it's actually seen, what's going on in the scene. So how are the failures occurring? But it really doesn't get at this question of why, right? Why did a failure occur is like really a root cause kind of question. And it's a very complex one when we're talking about black box policies, because quite literally many things could be going on. Your policy could be failing because it's taking in observations that differ from its training data, right? So it's like an out of distribution scenario. But the kind of failures that we'll focus on today from an interpretability standpoint are going to be like in distribution failures where there are potentially like root cause issues within the training data itself. When you start looking at the problem this way, you look at the training algorithm itself, right? Imitation learning or whatever algorithm you use, offline RL, as a black box that takes as input the data set and outputs for you a policy with some defined behavior. And then yeah, so it's kind of like a nested black box process. So you'd want to like start to be able to interpret your policy's performance as a function of the training data through the algorithm. And so that's like some context for this second work, CUPID, curating data your robot loves with influence functions, which was presented at Coral this year, and was awarded best paper at RSS 25 RoboEval workshop. And so some of the background there is quite standard. Again, we're talking about imitation learning settings where you've collected some demonstration data and you've trained your policy, for example, to complete a task like tying a figure eight knot on a cleat. And you train using imitation learning, right? So standard maximum likelihood objectives. And then finally, we have this third phase, which is common in all of our experiments, where we want to evaluate our policy on the real robot and see how it does. And you want to evaluate it based on a metric, usually success rate, but in this case, we'll call it expected return um, under the current policy. And the key observation here is that when you're using something like imitation learning, the performance of your policy is basically intimately linked to the demonstration data it's been trained on. This is sort of well known, and it's why when people do imitation learning, they so often, especially like in large scale settings, they start to like train their policy on various different subsets and then evaluate the policy and sort of try to hill climb based on vibes. But that's not really something that's like a principled or scalable approach to solving these kinds of problems. The question that we're asking is, what happens when you start to observe suboptimal behavior from your policy in deployment? We don't really have a way to look backwards into the training process and figure out and like debug our policies in a way that allows us to then improve them the next time around. So in other words, we're really good at going forwards, but going backwards is a much more complicated process. And that's the sort of the key research question. Then the thing that makes it like a lot harder is that your policies are being evaluated in closed loop. So it's different than robotics adjacent areas in machine learning, where it's like one failed prediction that your model has made, or like the failure is a result of one prediction your model has made. In this case, you have an entire rollout, and so which prediction do you attribute failure to, right? There's like a credit assignment problem there. And so our key idea here is that what you'd want to do first is sort of establish a relationship that goes from training data to your evaluation KPIs of interest, which for us again is expected return. And then the question is, how do you actually structure this relationship that goes through the training process? And our key insight here is that you'd want to do so using a predictive counterfactual framework, where you try to answer questions in a predictive fashion, such as what would happen to the performance of my policy if I chose to remove a certain training demonstration of interest, which entails estimating this performance counterfactual, which is the difference of the performance of your policy trained on all the data, right? So theta of d is like the parameters derived from like the entire data set, and the performance of your policy trained on all the data minus that demonstration of interest. And of course, like this is a great a goal and framework to reason about like the causal contribution of demonstrations toward performance. You can imagine if this difference is large and positive, it's basically telling you that adding demonstration tau to your data set is like improving the performance of your policy. So it's a good demonstration. While this is like a nice framework to think about these problems, you really cannot like approach this in a brute force fashion, because it would entail training your policy on all different subsets of data and doing an intractable number of rollouts. And so you really want to do this in a predictive fashion. How can you predict these performance counterfactuals? And in this work, CUPID, we propose to do so by making a first order Taylor approximation to this counterfactual. And so I'll lay out some of the math here for the sake of analysis. So we assume that our policy is trained using the behavior cloning objectives, and so we minimize the total loss, right? The loss across like all trajectories in our training data set. And then simply for the sake of analysis, right? Consider this perturbed objective where we have the original BC objective, right? So this is the loss on your entire training data set plus some epsilon weight on the loss of one trajectory of interest. So this could, for example, be like any demonstration in your data set. And so we're like simulating this idea of like adding an infinitesimal weight to just like one of your demonstrations in your training set. Then what we do in this work is we define this quantity called the performance influence of a demonstration, which really is the linear approximation, right? So it's the derivative of your policy's expected return with respect to that importance weight at training time. And what this is intuitively trying to get at for you is, how would my policy's performance change linearly if I were to slightly increase the weight on a training sample at train time? And then it's approximated at theta at epsilon equals 0 here because if you take epsilon equals 0, then you have the original BC solution. So basically, what we're saying is we're doing a sensitivity analysis around the BC solution, right? And then mathematically, via product rule, this breaks down into a product of two terms. One is the derivative of so the policy gradient, right? The derivative of your expected return with respect to the parameters of your policy. And then this second quantity, which you're perhaps less familiar with, which is the how does your policy's parameters change with respect to that increasing that importance weight. And that second term is actually pretty well known and studied in the machine learning literature. It's called the influence function, and there are a bunch of different tools for estimating this quantity that you can use sort of off the shelf, and they come with different advantages and disadvantages. But the key intuitive takeaway here is that this performance influence is essentially a linear approximation. A first order Taylor approximation to this performance counterfactual. And so there are a few things to like point out about this equation. The first is that like clearly it's doing some reasoning over the outcomes of sequential decisions because that's what your expected return is measuring. It's capturing a notion of performance as a function of like rollouts taken by your policy. So you have these many sequential predictions that the policy is making. Of course, the caveat is that you can't directly compute this quantity because it requires like computing the policy gradient requires like knowing the dynamics in this case and having access to like an unknown reward function. And just so you don't actually have a reward function that's defined, right? You only see the outputs. It's like +1 if the policy succeeds and -1 if it fails. And this is really different from the typical use of influence functions in ML literature, where basically all quantities can be computed. So typically what people do is they want to figure out the influence of a training sample on the loss of some test sample. They haven't gone as far, they haven't looked at the sort of MDP sequential decision making process to look at the influence of an entire demonstration on the closed loop performance of your policy. And the difference there is that for them, they can compute this influence function, the derivative of the loss on a test sample with respect to a training importance weight quite easily because it just entails computing like the gradient of your loss and the influence function, which can be estimated. And so for us, we need to do something a little bit more sophisticated to compute this policy gradient. And to that, we look to like policy, log derivative tricks underlying policy gradient techniques, which allow us to decompose this product into a tractable sum of influence scores. And so this looks like a big equation with a lot of terms, but we'll break it down because intuitively it's actually it's quite simple what it's doing behind the scenes. So first and foremost, we start by training a policy using behavior cloning. We then will evaluate the policy on the robot, and so we'll collect a set of M rollout trajectories. And we assume in this case that there is a human or there is some system in place that will label the end of the rollout, either success or failure, so +1 or -1 reward. And we'll use those rollouts to approximate the outer expectation. Okay, so we'll just take an empirical estimate of that outer expectation. And then for each demonstration in our training data set, we'll compute this performance influence quantity. So this equation is like what you would compute for each demonstration. And the way that you do that is you just sum over all the states and actions in your rollout, and you sum over all the states and actions in your demonstration trajectory. So tau hat is your rollout, tau is your demonstration trajectory, and you compute this inner influence term using existing influence function machinery. And this looks a little confusing, but really what this term is capturing for you is how does a training state action pair influence the likelihood of an action that your policy executed at test time. So if this inner term here is positive, it means that a training state action pair is like supporting higher likelihoods of that action that your policy generated at test time. And then what you're doing is you're weighting those terms, those influence terms by the return on that rollout. And so if a demonstration has state action pairs that highly influenced actions generated by the policy, and that rollout led to a success, then your entire performance influence for that demonstration will be a large positive number, right? Whereas if you have a training demo whose states and actions influence the policy, but it resulted in failure, so the R tau here is -1, you would have a negative performance influence for your demo. And so that's just to say that like higher number here means better demo, and then a reminder that this is like our final estimator for the performance counterfactual. And we think that there are a lot of ways that you can use this kind of tool to like reason about data and positive and negative transfer in data sets and things like this. But the first sort of immediate application that we looked at was data curation. And we came up with an algorithm called CUPID to do so, where we start with a training set of demonstrations, and we train our policy, and we evaluate it maybe over 25, 50, 100 rollouts. And then what our system can do is essentially take any demonstration from the training set, or it can take a demonstration from a newly collected set of data. Like maybe it's a streaming scenario where there's constant data that's coming into your workflow. And the performance influence essentially does this projection of these demonstrations onto the space of like that downstream KPI that you're interested in. And so you could see that like some of these demonstrations are if you were to like if add them in or like remove them, your policy would move in the direction of like higher likelihood of success or lower likelihood of success. And then this allows you to basically rank your demonstrations based on their performance influence. And then finally, you can curate your data set by selecting the top K demonstrations based on these scores. And then, hopefully, and we'll get to some of the conditions here. Hopefully, that results in a policy that is better able to achieve the task. And then the key takeaway is that by doing this, right, you're essentially curating a data set that most strongly influences the test time success of your policy, not some like validation losses or training losses. Cool. Um, and so are we the only ones studying data curation? No, there were a few works that came before, and I think there have been a few works since. The first on the left is one called demonstration influence, which uses a an offline metric called mutual information to score demonstrations. And in essence, what this algorithm is doing is it's upweighting or like it's assigning a higher quality to demonstrations where the actions are like really easy to predict given states, right? So the mutual information between states and actions is high in that setting. But again, completely offline. So this is something you would run before you even train a policy and before you like evaluate a policy. In the middle, you have an algorithm called demo score, which involves training policies on your training data and evaluating them. The difference is that it trains a classifier to distinguish uh, states from successful and failed rollouts at test time, and then it runs that classifier on all your demonstration data, and essentially is trying to get at this idea of like states that were bad at test time are probably also bad at training or like are bad, within the training data. And so you should remove states that like look similar to test time failures. And then with performance influence, this is what we just covered. And so, what are some of the things to think about when it comes to like these different data curation algorithms? Well, the first is that um, on the left you have a manually defined notion of quality. So someone has, imposed that your ability to predict actions with high accuracy given states is like a good property of your data set. And so if you curate with respect to this property, it's like always going to be good, which is an assumption that may not hold in the general case. Um, Perhaps like stochasticity and variance is for some reason good for your task, right? So mutual information may not be the right metric. Whereas for demo score, it's sort of similar, right? But in this case, it's more getting at this idea of like similarity between states at training and test time. Whereas for CUPID, what we're really trying to go after is like causally connecting training data to your true performance quantity, which is your expected return. That is like the true performance quantity that people are always optimizing when they're doing RL. And it's really the thing that you care about most in terms of policy performance. Um, and then, of course, like this is a completely offline algorithm, DEMIM, so there's nothing causal going on here. Um, Demo score is bypassing the problem of like doing causal analysis because it's using similarity instead. And of course, like by like setting up this problem from the beginning as predicting counterfactuals and assessing the causal impact on downstream likelihoods and behaviors, our method is like causal by construction. And then the thing that's like good about DEMINF in practice is you really don't have to like evaluate your policy on the robot. You don't have to train a policy. It's just something that you would throw into your pipeline like beforehand. With demo score, it involves taking multiple policy checkpoints throughout training and evaluating all of them. And so you have like n times, where n is the number of checkpoints, the cost of CUPID, where CUPID you just take the last policy checkpoint and you evaluate that. And so what are the scenarios that we studied? Uh, we focused on three scenarios. So the first was this figure eight task, where we collected data sets with different quality tiers. So you have some demonstrations that like solve the task in a slower but like more smooth motion, others that solved it faster, but perhaps made some compromise in terms of like the smoothness of these trajectories and so on. And or like didn't go as wide. And so, at test time, you may have a policy that like, gets stuck around like the edges or doesn't go as like wide enough because it wants to complete the task faster. And the goal of curation in that setting is to be able to figure out which one of these demonstrations are like adversarially affecting the policy's performance. Um, and then in this work, we actually look at two different curation settings that are not commonly explored. This second one is a multi-strategy data set. And so your goal here is to like put the blue recycling bin underneath the rack. And there in the data set, there are two different ways of doing so because maybe you have like a team of data collectors and people have different preferences for solving the task, right? Some people prefer to just slide the box all the way under, which is strategy one, and others may prefer to pick it up and place it before like tucking it in at the end. And then the key thing, the key observation there is that like at test time, these strategies are not like equally viable. So if you have a distribution shift to the box, to the mass distribution of the box, for example, if now like some of the things contained in the box are heavier than others, one of these strategies is rendered unreliable. And so you want to be able to like at test time start to figure out which one of these strategies is generally more robust. And then finally, in the hardest case, we look at data sets that have spurious correlations between features in the scene and demonstrated behaviors. And so this is like really tough to disentangle for curation algorithms. And it's not a problem that it's a problem that's becoming like more and more discussed in imitation learning, but it's really like studied more thoroughly in like large scale image classification and whatnot, where you have models that make predictions based on spurious features, like an image classifier saying that there's like this is an image of a cow just because it's like an open field of like green grass, right? But what we have here is a data set that has like a few different cases. The two main ones are you have many demonstrations that have a dark background, but also have two books that are stacked here. One is the yellow book, which is the target book you want to retrieve. And then there's this red book, which is, or like this pink book that is stacked on top. And the idea here is that like when there's a stacked book, you need to pull the target book out in this like vertical motion so that the stacked book doesn't fall out. And that's like a pretty hard motion to execute, even if you've like done a lot of data collection. And I can tell you this from firsthand experience that like I almost broke this shelf multiple times. Um, but in the second case on the right hand side, you have a light background and more often you have a light background where you have just a single book. So you don't have a stacked book. And when you have a single book, you can pull the book out in this like very easy to execute horizontal motion, because you don't have to worry about anything falling out as a result. And then the question to ask is, what happens when you have a light background but a stacked book or a book stack? Will the policy attend to the light background and execute the incorrect horizontal pulling motion, or will it look at the attend to the stacked books and execute the correct motion, right? So this is a case of like spurious correlation built into your data set. And depending on like on certain variations, we'd find that the policy does execute the wrong strategy oftentimes. And then just to give a sense of like qualitatively what curation did in these settings, CUPID, ours, deminf, which is our strongest baseline in the middle, and then random. Random is a sort of naive baseline where you just randomly drop out demonstrations to see what happens. Um, you find that both CUPID and deminf do quite well when you have this mixed quality data set. So you have some samples that are like uh, by human standards higher quality than others. They're able to identify those demonstrations. Random, of course, doesn't break that issue in the data set. However, on the tuckbox case where you have multiple strategies, only CUPID is able to really uh, causally identify that the sliding strategy at test time is is really the issue here when you have a distribution shift to the box to the recycling bin that you're trying to tuck under. A deminf in this case, because it's an offline metric that's based on mutual information, it actually prioritizes the demonstrations that appear smoother, which are these sliding ones. And so it does the opposite of what you'd want it to do. And then finally, for bookshelf, when we evaluate the robot and we see that the policy is attending to the wrong feature, um, when we curate with CUPID, it's essentially able to disentangle that spurious correlation and retain more demonstrations that have the white background, but like a stacked book, which makes the policy attend to that feature a little bit more in subsequent training and evaluation stages. And then deminf does something very similar to before, where it's like almost always prioritizing this horizontal pulling motion because it appears smoother and easier to learn for the policy, even though it's the wrong one to execute, given the setting.
Um, sorry.
Yeah,
So in this, in previous example that you gave, so you
yeah,
do some rollouts, relabel them as success and failure,
yeah.
and then retrain it. Is that correct for Cupid?
So what we would do here is we have a deployment setting fixed. So in the deployment case, the background is always white.
Right.
And then there are cases where, like maybe we do 25 rollouts, and there are cases where there is a stacked book and cases where there are not. And in cases where there isn't a stacked book, the policy will just pull horizontal and it will succeed, right? So those rollouts are labeled success. The ones where there is a stacked book, if the policy executes the incorrect strategy and the book stack falls, those rollouts are labeled as failure. What we do is we then trace back, right? We trace back both those successes and failures to each individual training demonstration, which allows us to figure out which training samples, which training examples are causing the policy to execute the failing strategy at deployment time. And so what this means is that like the demonstrations that have the white background but no book stack, those end up getting like deprioritized because basically they're reinforcing the policy to like attend to the white background and not to the stacked book. And so what you're doing is basically like doing some deployment aware rebalancing of your data set to break the spurious correlation. Yeah, that's basically what's going on behind the scenes.
So it seems like we use an extra signals in the form of these rollouts that you collected, and then you retrain your policy using these extra signals. I wonder, is that the same thing you do for like deminf, or deminf is just trained on a static pre-trained data set?
Yes, absolutely. Deminf is just trained on a static data set. Yeah. So that was kind of this point that I was trying to make with deminf, which is, like you could view it as an advantage because uh, you don't have to do rollouts. But then what we're trying to claim here is that if you do rollouts and you have this additional signal, it allows you to better curate with respect to downstream KPIs. Cool. because I want to leave time for more questions, I will go a little bit faster through this part. The key takeaway quantitatively from our experiments is that CUPID and DEMIV actually do quite comparable on settings where you have on settings where human perception of data quality align well with what is actually needed to succeed at the task. However, CUPID is really the only one that is able to give you like uniform improvements across different kinds of settings where data may be harming your policy's performance at test time. And that simply falls out of the fact that you have set up your problem in a way where demonstrations are related to downstream performance. And then finally, we have this sort of ablation we did where we took data sets curated by CUPID for single task diffusion policies. And we use those curated data sets to fine tune multitask Pi0 VLA. And what we saw there was that you can actually get improvements on the VLA as well. Even using data sets that were not curated specifically for the VLA, but they were curated for the diffusion policy across these two tasks. And the thing here is that the performance improvements aren't as drastic as we saw for the diffusion policies because CUPID is not a curation algorithm that is like policy agnostic. It is curating data sets that would be best for the specific policy class and the weights because it involves computing like gradients and Hessians of that policy. That said, there is some transfer in the idea of like what is good for one policy is probably going to be good for another policy. And so the performance improvements are a little bit tempered in this setting, but still notable. In the interest of time, I'm going to skip through this and go straight to analysis of RoboMimic. And very quickly, we looked at the RoboMimic mixed quality task suite, where you have like a few different tasks. We chose 3 of increasing complexity, so diffusion policy performance goes down from left to right. And these data sets come with manually labeled demo quality scores. So each demonstration in these data sets have a label that is for lift and square falls within like the low, medium, high quality tier. And for transport, there are 6 quality tiers because there are 2 demo collectors working together. And so you have like low, 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 medium, high, high, and like all combinations in between. And then the key thing to point out here is that like these are, human perceived quality, right? So this could be some form of quality assurance where people look at demonstration data sets and sort of rank these demonstrations by how good they think they look. And what we do is 2 kinds of plots, really. First, we have sort of data quality type plot where we look at how the average quality of the data set either increases or decreases as we filter more and more demonstrations, right? So we'll basically like remove 100 demonstrations, take the 200 that are remaining, and then compute the average quality using their ground truth quality labels. And then these lines represent different algorithms, right, for curation. And then what we also do is a policy performance plot where we take those curated subsets, we retrain the policy, and we see whether performance has like increased or decreased as a result of curation. And I think like the key takeaway here for us was that perceived notions of demonstration quality don't always correlate with what's truly best for your policy. And so here you have you have this purple line where you could see this is DEMIV. The data quality trends appear much stronger for demonstration for DEMIV. As you curate more data sets, you have a steeper increase in the percent increase of your data set quality as measured by human terms. Whereas CUPID in orange is like clearly curating data sets of lower perceived human quality. But when it comes to policy performance, you start to get like improvements from CUPID that like exceed at some point DEMIM's performance. So that's kind of the key takeaway there. And then in the interest of time, I will just skip. I'll skip to the end of the presentation. We can discuss any questions that you may have.
Thank you, Chris. Great talk. I have some questions about Cupid. First question is, it seems that you now define the reward function as 1 if the whole episode is success, otherwise 0. And will you consider like any demonstrations that can lead to subtask success, but not whole task success? Like if you want to execute a long horizon task, and some demonstrations make for example, peak place tasks make peak contribute peak more more than contribute to place
Yeah.
or something like that.
Yeah,
Did you try that?
absolutely. I haven't tried it in experiments, but essentially the theory extends naturally to those cases because what you would be looking at is simply a case where your returns are like stage wise, right? So it's not just a sparse like +1 -1 at the end of a trajectory, but if you executed the first pick correctly, but then like messed up on the place, you might have like 0.5, right? As like the return on that trajectory. So the idea there is that like you can define this reward function however you want. That the algorithm should that's why we try to derive things in terms of expected return, because expected return is a quantity that makes sense in the context of like sparse rewards, also dense rewards, stage-wise rewards, and so on.
I see. And the second question is, it seems that this method is also deployment environment specific. So you
Yeah.
assume you have a testing, and does that say that you are not targeting at making the policy more generalizable, but make the policy work better in that specific scene?
Yeah, absolutely. That would be true. And so then, one of the things that we try to think about is like, what is the killer app? The killer application for something like this. This is like probably not something you want to apply over like at the pre-training stage, right? But maybe if you're trying to like squeeze out every inch of performance in like some deployment time post-training phase of VLA, maybe then this is the right tool for that problem. At the same time, it's worth noting that like Cupid it's doing a first order Taylor approximation, right, to this performance counterfactual.
Yeah.
It doesn't account for like weird coupling effects between different demonstrations. It's treating demonstrations as like independent. And what that means is that if you have, let's say, clones of demonstrations that do the same thing, but they're all ranked as very high, Cupid won't naturally it won't naturally like preserve some diversity in your data set. You could end up with like if you have a really adversarial data set where like Cupid just retains all demonstrations that look exactly the same, and then that's also like not good for your policy, right?
Yeah.
And so I think in the future, like looking at how to sort of combine these performance influence metrics with some like diversity metrics, right? So that like performance diversity trade-offs and things like that could be like an interesting line for continued work.
I see. And my last question is, have you thinking about not attributing the success or failure reason to each training sample, but to the like factors in the training sample? For example, if you attribute back to the training samples, and most samples that contribute high have like light background, and that means
Yeah.
maybe the policy is not robust against background color. And if the high contribution training samples have some features like lighting, like some kind of lighting. and it's very diverse, maybe it illustrates that the policy is already robust against the lighting condition. And then it can be used to guide you how to collect new demos instead of reweighting the existing demos. Then maybe the next thing to do is to collecting more demonstrations with more randomization of background color. And I read your paper, it seems like now you assume existing new data set holding there. And you can curate some subset of that new data set and merge into your existing data set. There is a way to use CUPID to assuming there is no new data, and you can tell the users any guidelines to collect some new data to merge with the existing data.
I think this is a really cool idea, and I hope somebody works on it. I think it's really interesting. Yeah. So it's basically like, I mentioned that we think that there are many things you can do with this kind of machinery. We ended up just focusing on curation, but I think broadly speaking, right? I think like interpretability as a topic in general is something that I've seen like a little bit more work spur up recently, and yeah, I think like using these scores to pull out like some more interpretable features in order to guide collection. Like these are interesting problems I hope people work on. Yeah.
Can you so can you talk about the computational challenges in like CUPID, and like if I had like a much bigger data set?
Yeah. Yeah. So what does it basically entail from a computational standpoint? Basically, it requires you to compute a single gradient term for every test transition, state action pair, and every training transition. And then using the influence tool we use, which is a method called track, the inverse Hessian here is so the Hessian is not actually the second derivative of the training loss, but it's actually a Gauss-Newton approximation to the Hessian, and so it's like an outer product between the first order derivatives, and so that makes it cheaper. But in essence, the compute cost is roughly the same cost as training the policy in the first place, which is something that's fine for post-training, right? Because you could post-train a VLA on a 5090, right? And so you could run this again overnight and get your scores, but it's definitely not the thing that you can do at the pre-training scale where companies are paying millions in compute costs to pre-train their policy. So I think compute cost here is a thing. When you're scaling to larger data sets, though, I would say that there are other ways maybe you could think of this where you no longer compute the influence for every single demonstration, but maybe you would try to like approximate the influence of subsets via like random samples taken from those subsets, right? So you can do like subset level influence approximation, which is in future, one of the directions that I outlined for future work is, can you extrapolate this to larger data sets by doing coarser subset level analysis, right? So there may be ways to make this more tractable.
So can you go back to that equation again? I just had a follow-up question.
Yes.
You mentioned like, let's say if it's approximately equal to post-training, a post-training compute, right? That you have to spend in order to calculate all the gradients. Is the Hessian like scalable with the size of theta? Like the Hessian calculation, because VLAs are much, much bigger than, I'm guessing, the policy that you use for a single task.
Yes.
Would you say that the Hessian would still like scale as much, or do you think that you could see as a potential bottleneck to that?
It depends on the way that you compute the Hessian. For like earlier versions of influence estimation for deep neural nets, where they actually like they try to compute, for example, second order derivatives, like agreed, huge issue. Here the Hessian is using track. it's constructed from first order gradients. And so you never actually have to compute like second order gradients for the model. The so there are ways to get around it via approximations.
Mhm.
At the same time, some tricks that people have done in the past is to only consider a subset of your model parameters. So if you have like a VLA which has this large LLM backbone, you could compute influence on just that the diffusion head, if you see what I mean.
Yeah.
And that is definitely a possibility. I think uh, this was a collaboration with TRI, and I think that they're looking at applying it on their LBM models, right? So there are ways that you could scale this up to larger models.
Makes sense. Yeah, thanks. No one
Cool.
has a question. I had one more question. Uh, in the initial part, you mentioned about splitting failures into categories.
Yes.
And you discussed two categories. Do you think like that's like all encompassing categories, or I guess question prior to that is like, how did you decide these two categories on? Was that based on the failures you saw, or do you think that this sort of is the most can encompass every different types of failures or most failures?
Yeah. Uh, I, uh, I think I would definitely sway away from asserting that these categories are sort of like umbrella
Yeah.
over all kinds of failures. I think the way that we approach this is first by like trying to define what we mean by failure. And it's actually a little weird to think about. Like there are some cases, there's some tasks where like the criteria for failure is a little bit more clear, right? Like if what you want to do is something with a bottle and you have a robot that is tabletop fixed and it like accidentally knocks the bottle off the table, then like you failed, right? Um, but what we went with was a sort of general definition for failure, which is simply not completing the task within some maximum defined horizon for that task. And so under that category, like if timeout hits and you haven't completed the task, you failed. And so in essence, in theory, you could catch all failures with with a VLM by just asking it at the end, um, did the task is the task succeed or not, right? So if you have like a final success classifier at the end, you could be catching failures that way. But I think where the categories came from is thinking a little bit more about like where that some kinds of failures happen faster than others. And so can you come up with like categories that allow you to catch things um, in the shortest amount of time possible, right? Um, rather than thinking about all the different kinds of failure modes. And so that's where we came up with this erratic failures and temporal consistency kind of ideas, and then task progression failures as a sort of like catch as much as you can type of fallback monitor. Um, but yeah, I think we're thinking a little bit more whether you can like define more groups that allow like more efficient divide and conquer strategies.
So I guess like you mentioned this was divide and conquer, but can you say that category one is a subset of category two?
Yes, you can. Yeah.
Okay. Nice. Thank you, Chris, again. And we'll see you in the one-on-one session.
Thank you. Thank you, everyone.